All right, this is going to be an example problem looking at relativistic momentum. We're going to look at electrons. So electrons have been used at low speeds in old television sets, and they are used at really high speeds in cancer treatments. We're just going to kind of compare how does the momentum, the relativistic momentum of a electron at lower speeds compared to its classical momentum, and then how does it at higher speeds. So again, just getting comfortable with this idea of classical momentum. So when doing so, we want to remember that classical momentum relationship is mv. When we look at relativistic momentum, we're going to take into consideration that lowercase gamma, right? So 1 minus v squared over c squared, all under that square root. So 1 over that value. Okay, so let's look at how this compares in our two cases. In a CRT monitor, we have the speed of the electron is equal to 4.00 times 10 to the 7th. So in the TV, our momentum is going to be mass times velocity divided by the square root of 1 minus 4e to the 7th over 3e to the 8th, quantity squared, and that equals 1.01 mv. Now mv is our classical, so this tells us that it's 1% more momentum than if we consider the momentum of that electron in classical sense. What about in our cancer treatment? So in the treatment case, well, the same relationship holds, right? So we have mv over the square root of 1 minus v squared over c squared, or the quantity. So that's mv, I guess I didn't write the equation up last time, of the square root of 1 minus, and in this case, our object is moving at 0.98 c over c, and it's that whole quantity squared. And when we calculate that out, we get 5.0 times mv. That tells us that the electron in our cancer treatment has 5 times the momentum as if we just looked at it classically. So, getting used to looking at relativistic momentum, appreciating that when we're moving really, really fast, that momentum no longer is just our classical value. Now, I mentioned in the introduction that conservation of momentum is maintained, and it is, as long as, remember, we're considering those relativistic velocities. All right, good job.